Meters squared, right? Yeah, I just. Okay. So yeah, for the syllabus, maybe I want this to be recorded. I'm not going to go through it because I assume you can like read that thing on your own. If you have any questions, I'll be very happy to answer those. We'll have 7 homework assignments. Those are very important. I really think homework is important for this class in particular, probably most than any other class you've taken before, because topology is very abstract. That's pretty much the point of it. It's like you can do, I don't want to say geometry, but kind of, but in pretty much any set that you like. So the idea here will be something like, what you do for the real numbers, there is this notion of nearness. You can also do that on the plane, on the 3-dimensional space, and so on. What we're going to do is we're going to do something similar, but on any set. So that's essentially what a topology is. I need to convince you of that. That's not going to happen today, but that's what's going to be happening here. So very general, very abstract, and it's a lot of fun. So that being said, let's just start. Today, what I want to do is just a review. Most of the things I'm going to say today, you should kind of know, but I want to like set up some notation, and I want to be sure that everyone here is following. If you are too bored, you can like let me know. I'll be very happy to speed things up. If it's the other way around, you can also let me know. So let's start with something that I like to call naive set theory, because it's not really set theory. So what's the idea here? The idea is we want to study sets. What a set is, it's not something that I really want to define. So I'll say quotation mark definition. So a set for us is going to be, a set is a collection of objects. Okay, that's not a definition, but. So here what I'm defining is what a set is. So usually what I'll do is I will try to like emphasize this thing that I'm defining. This is not a definition, but here I'll be defining what a set is. And the important thing about a set is if we want to say, we say that something that's an element, let's use small a, is an element of our set A, and we're going to write A belongs to A. So this is a very important thing. And the thing about sets is we are not going to go through the axioms here, but if you have a set, essentially what you can is decide if something is an element or if it's not. That's pretty much what you need to do if you want to do set theory. So otherwise we just write A is not an element. And then if you have two sets, we use A is a subset of B. So this means denote if X is in A, then X is in B. And this means A is a subset of B. Are we okay with this so far? So of course, sets on their own are not that important. We have operations, so basic operations. We have the union of two sets, A union B. So here we're going to put all things. This is what some people call the set builder notation. I'm going to put all things which satisfy something, and the something is either X is in A or it's in B. And then the intersection is things that belong to both. And then finally, this one is kind of funny, the difference. So I'm going to try to use set minus notation here, but probably I'll forget about that and just go with minus. So this is X such that X is in A, but not in B. Okay, any questions about this so far? Yep.
Are and or are those proper like mathematical terms or?
Right, so this will be a logical or, and this will be a logical and. Yep. Now, I don't want to say too much about this, but if you have like an ambient space, sometimes called a universal space, instead of doing a difference, you can define what's a complement. And then the difference is intersect with the complement, right? But you need like an ambient universe. And I don't want to say universal set here. That's what's going on. Okay, so next thing I want to say is how these things behave. So some properties, or maybe before saying how these operations behave, I want to say there is an empty set. So there is an empty set with no elements. We need to assume this is the case. There is an empty set. Notation is that with no elements. And pretty much by abstract nonsense, it should be a subset of any other set. Because if I go up, this is always true. Because there is no element here, hypothesis false, so condition is true. And that's the first fact. And then the one that I actually want to say is we have associativity here. Associativity. If you have three sets, then there's two ways for us to compute their union. Remember, union only takes two sets as an operation. So you can either do that, or you could do this. And you want the answers to be the same. Since these two things are the same, and also for intersection, so I could also write an intersection here, intersection. That being the case, we can just write a union of three sets. Same thing we do with numbers. In principle, you only know how to add two of those. If you have three, there's two ways of doing the addition. The answer is always the same, just denote this. Okay, then we can distribute. So distributivity. If you do A intersects B union C, that's A intersects B, union A intersects C. And now if you do A union intersection A union B intersects A union C. Now we have what's called De Morgan's laws. If you do the set difference here, so sometimes De Morgan's laws is just like the complement of a union, but here I'm not defining complement because I'm just doing set difference. So I'll need to do A minus union, so B union C. I'll be A minus B intersects A minus C. And then if I do A minus the intersection of A minus B, union A minus C. Are we okay so far? So this is, let's say, not very interesting or not very new. These things we should be familiar with. Now, families of sets. So the idea here is, so far we've been operating with two or at most three sets. Now maybe you want to have a collection of sets. So let's take family. Let's use curly A. Family of sets. What I mean by this is it's a set, but each element of curly A is a set. In this case, we can define the union over things in the collection. This is just going to be things that belong to something in the collection. So X is in A for some A in A. Are we okay with this? That's what it should be. An intersection. Now, as I'm writing this, I wanted to think, do you understand what I'm doing here, the notation? Do you have any other notations that you'd like me to use? Yep.
So this kind of acts like a sum, right? Except it's A with one index to the union of A with index.
But the thing that's one good thing about, so you probably have heard this before. So what we're doing is kind of some algebra of sets. And if you're doing that, then union is sum, intersection is multiplication. But the thing about sets is they are way better than numbers in some sense. For example, you can do the union of any amount of sets, but you cannot do the sum of any amount of numbers. You need to have an order, you need to be careful about like intersections, and you need to be careful about how things converge and so on. But with sets, you can do pretty much whatever you want. So way better than that. Are we okay? These are families. So let me just say distributivity and De Morgan still hold. So for these families.
Okay, the two capital A's are different, right?
Like, let's see, these two.
Yeah. Or A and A.
Yeah, these are different. Maybe let's use, yeah, that's a good thing. Let's use X. Let's use X. Oh, maybe X is another bad thing. Let's use, no, but I'm using that for other things. Let's use Y. It should be capital Y. Y, and then X is in Y, Y. Okay. So what I'm saying, when I say things that are not precise, maybe you should try to make those precise. If you're following the intuition here, it's a good kind of question. Can you make this statement precise? Any questions? So if you've been playing with this, usually these families don't present like this. Usually they present like this. So usually in practice, we have like an index set. So the family curly A is indexed. So what do I mean by this? Indexed. This means there is some other set, of course, called a set, an index set or set of indices. There is a set. I'm going to use capital lambda for some very historical and weird reasons, such that my collection of sets, A, can also be written as A sub alpha, where alpha is an element of the index set. And usually that's what an indexing is. It's just rewrite things in a different fashion. And if we use this, so with this notation, or with this indexing, we introduce this shorthand notation. So we compute the union over alpha in the index set of A alpha. And that just means what we denoted before by, oops, I forgot my Y here. What we denote before by Y in A of Y. Yep.
How do we pronounce that symbol?
Oh, this is capital lambda. And some other fun thing that I can do. So this is probably a good moment for me to slow down and say, I would really like you to try to typeset your homework. If you're familiar with LaTeX, that'll be very helpful for you, not for me. Also for the grader probably, but not for me. So if you like to do that, I'll highly encourage you to do that. If you're interested in going with LaTeX and you don't know how to, you can send me an email. If I get at least 3 emails, I'll record some sort of tutorial how to typeset your homework with LaTeX. So in LaTeX, this is \capital lambda. If you don't understand what I'm saying, no worries. That's not part of this class. Okay. Are we okay? Yep.
So capital A sub alpha.
Uh-huh.
That is different than Y. Because before you replace capital non-curly capital A with Y. So could you write that as Y sub alpha, or is that too confusing?
could also say, but here I'm saying these things are called A sub alpha. So if I want to say Y here, I need to say. No, this A is not curly. No, yeah.
So we couldn't.
For me, curly means there is this thing here.
It would be incorrect to write to replace A sub alpha with Y sub alpha, for example.
If you do that here, absolutely okay. And then you also need to do that here. But you need to be consistent. So these are just variables, but can get confusing. Now here, variables, everything are variables. So this will be like having a sequence. Instead of using AN for a sequence, you could use BN for a sequence, but you need to be consistent. Okay, are we good to go? So of course, I also have a version of this with intersection. Okay, so that's pretty much, well, yeah, maybe let's say for the moment, that's all basic set theory I would like you to do. And for this class, this thing of, so what I just wrote, this is sometimes called an arbitrary union, because you are taking a union over an arbitrary set, or an arbitrary set. These things are very important. We're going to use those next class. So absolutely important, also intersection. So operating with arbitrary families of sets is very important for this class. Now I want to go to functions. So some basic functions, maybe chart them, I don't know. So kind of embarrassing, but a function is, so a function from set A to a set B is sometimes something that's called the rule of assignment. Rule of assignment. And now let's be more precise. So if we want to be more precise, a function like this from set A to set B. So remember, this thing is called the domain. This thing is called the codomain. Those form part of the definition. So if you want to be formal and precise, well, for us, a function is going to be a set. It's going to be, it's a subset. I'm going to use the same letter F of the Cartesian product. Are you familiar with Cartesian products? Do you want me to say something about that? How do you feel about Cartesian products? Are we okay? Okay, so it's a subset of a Cartesian product. And what we want here is, we want it to have properties. So the properties is the following. First one is, for any element in the domain, there's always going to be something that's going to map F to A2, sorry. There exists some B in B such that instead of saying F of A is B, I need to say A comma B is in F, because for me, F is a set now. And the other one is, so I'm assigning A to something, and I want that something to be unique. So how do we say that? We say, if I'm assigning A to two things, B and B prime, so I'm saying here, F of A is B and also B prime, then B needs to be B prime. And remember, that's how you say things are unique in math. Then B is B prime. So what this is telling you, in other words, for each A, let's say, in the domain, sometimes called for each input, there is a unique output. So exists unique B in B with A comma B in F. And this means makes sense to write for that particular B. We say that guy is going to be called f of a because only depends on a. So that's what a function is. So this is kind of the upshot here. Because of these two properties, it makes sense to write f of a. It's a well-defined thing. It exists and it's unique. Okay, so some notation here, also extremely important. Not really for the first part of this class, but yeah, at the moment so we're going to define what a topology is, and then after that, we're going to start discussing functions. So this notation is going to be extremely important. So if you have a subset of the domain, let's call it U, we're going to denote f of U is going to be a set. So I'm applying the function to a subset of the domain. Might be familiar with this. This is going to be do f of a, but only to things in U. If you have a subset V of the codomain B, then pre-image. So this is sometimes called direct image, and I'm going to use this word. And this thing now is called pre-image. And I'm not saying the function is a bijective function. I'm not saying there is an inverse. I can define this always. So it's going to be all things in A, such that when you apply the function, you land in B. And this is what's called the pre-image. So this first guy is a subset of the codomain, and this guy is a subset of the domain. So have you seen these things before? So if you've seen this, questions I like to ask here is usually, now we have functions, we have set operations, we need to understand how they interact. So question, if you do f of U union B, and you do f of U union f of P, what's the relation here? Are these two sets equal? Remember, equal for sets means both are subsets of the other, or do we only have one inclusion? What's the case here? Same for intersection. So if you do f of an intersection and you do intersection of f's, what's the relation? Are these two guys the same? Is one a subset of the other? Is it the other way around? Do you remember these things? So I promise you, you will become familiar with this stuff because that's what we're going to do in this class. Now, we don't have a homework due this week because we don't have class on Wednesday. So what I'm going to do instead is today I'm going to upload some sort of review sheet for you. And I will ask you questions like this. And I will ask you to prove things. You will not have to hand this in. It's just for you to try to remember. I'm not saying things should be easy for you, but shouldn't be very complicated. Should be things that you know and now are trying to remember. So you can do that for functions. And now the only good thing about going with the iPad is that I get to copy this. I need to paste. So notice here I'm using U and V as whatever I wanted them to be for the questions to make sense. I'm going to use F inverse now. Same set of questions. And let me tell you, the upshot here is pre-images are very good. Everything works nicely with pre-images. Direct images are not so good. So that's the upshot. So pre-image is great. and we don't want to be rude, the other one is not great. Yep.
When he's looking at it, you think that the relative with the direct that you can relative issue where two inputs have the same output, right?
Absolutely, yeah, yeah. That's what I want to discuss now. So image is. So this is kind of a spoiler. Image is great if the function is injective, and that's what I want to discuss now. At least introduce the definition. But functions are very rarely injective. So yeah. So those are some questions you're going to have to answer. Maybe let's kind of remember this definition of sorts. So let's take a function. Usually in math, when you say let f from a to b, you assume that's a function. You don't even need to say it's a function. So take a function, then this thing is injective if whenever you have two things. So let's say for any a and a prime in a, the domain, if the function collapses these two values, then that's because they were the same to begin. So remember when you see this, maybe this you don't need to. I don't need to say this, but that's a very easy to work with way of saying you don't get to collapse two different things. But it's a sophisticated statement. It's doubly quantified. It's a conditional statement. But that's what an injective function is. That's the only way you have to decide if something's injective. And the other one is it's surjective. Whenever, so someone told me once, well, I mean, I know this is a famous quote, a good mathematician is a lazy mathematician. So that's what a surjective function is. Of course, this is not a useful definition. But if you go back and remember what this means, you will see these matches with your definition of surjective function. Okay. And then finally, your function is bijective if it's both. So from my point of view, you have sets, you have functions. Those are very important, but you need to define compositions because that's how you operate with functions. We know how to operate with sets. We need to know how to operate with functions. So composition. Here, mostly what I want to do is I want to introduce you to the notation that I'm going to use for composition because I just like to use it. So suppose you have two functions, f from a to b, and then g from the codomain of f to some other set c. We get a function called the composition g of f from a to c. It's a function given by, if you do g of f at an arbitrary element of the domain, what you need to do is g of f of a. And the notation I like to use here is, I like to say things like I go from a to c to b, sorry, using f, and then I go from b to c using g. And you'll see me write things like here, a element maps to f of a, and now this element will map to g of f of a. You don't need to use this, but it's very convenient. So something that's extremely important is that composition is associative. So let me write that. Again, I'm being imprecise, but if I say something like this, you should try to make it formal statement. And that's extremely important. And the other thing that's important for composition is we have identities. So if you take any set, for any set, something very naive, there is an identity function that I'm going to denote by I sub a. So it's a function from a to a. And this function is going to take a to a. So this is called the identity. And if I go back to my notation before, when you do, what can I do? I can first do identity of A and pre-compose with F. That's going to give you F. And I can also pre-compose identity of B with F. That's going to with G, sorry. That's going to give G. Okay, that's composition, identities, very important piece of information. Yep. Probably, yep. Thank you. Thank you. So we know how to compose. We have identities. And now, yeah, maybe let's say this fact. Function f from A to B is bijective. If and only if, so this is a fact that maybe you should know how to prove. If and only if there is a function, and I'm going to use F inverse again. So this symbol gets abused a lot from B to A, such that when you do F inverse of F, you get the identity of something that should be A. And if you go the other way around, and if you do F of F inverse, you get identity of B. So this is telling you A and B are pretty much the same set, but they are labeled in different ways. That's what this is telling you. Any questions? Let's say some very brief words about cardinality. So the idea here is we want to count sets. So to begin with, I'm going to say, maybe before I do this, I need to say, there is a set of positive integers. Positive integers. 1, 2, 3, blah, 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 blah. I'm not going to discuss much about the definition of these guys. You can see the textbook, which, by the way, I'm going to use a lot, the textbook for this class. So if you don't follow what I'm saying, you can go to the textbook pretty much for everything. I don't think Mancurs uses my definition of function, but everything else is pretty much the same in the textbook. So that's the set of positive integers. We know this thing exists. And now I'm going to say that the set is finite. It's finite. Maybe I should say what the set is called. Set A is finite if either empty, namely the empty set, or there exists some positive integer k and a bijective function from A to the set of the first k positive integers. And very importantly, if that k exists, it's unique. So in that case, you say A has k elements. So that's what a finite set is. Now I want to say what's an infinite set. So a set is infinite if it's not finite. Make sense? Next thing is what's a countably infinite set. Countably infinite set is a set that's going to be either is a set that's either finite. No, it's a set A because I'm saying countably infinite, such that there is bijective function from A to N. And then you say that A is countable if it's either countable infinite or finite. So sometimes countable is used for what I'm calling countable infinite. Yep.
Well, I'm gonna ask, like, isn't Q also countable, so there's like a Q, but then you still make one Q to add, right? So then
Right.
you still.
So here, right, here we have integers, rationals. We have like 2 rationals. I'm going to say something about that. And then finally, A is uncountable. And this is the case if it's not countable. And here we have, for example, the real numbers or the open interval 0, 1. We have the power set of the positive integers. That's Cantor's theorem. Don't really need to be familiar with that one. That's good to know. Are we okay with these? You remember these things? Okay. So some facts I want you to know because at some point I might want to use this. So facts. The first one is, what's the first one? Yeah, if you have a subset of a countable set of countable, it's going to be countable. Then the other one is, so these things are theorems. If you do the countable union of countable sets, it's also going to be countable. What do I mean by countable union? What do I mean? Yeah. Absolutely. So what I mean by this is I'm doing something like union over A alpha of A alpha, and here where alpha is countable. So this is what this countable means. And this other countable here means each one of these is countable. Can you distinguish these two colors? Okay. And that's the second one. And then the third one is if you do a finite product of countable sets is countable. And the good question for you might be, is that true? Is that still true if I say countable product instead of finite? Could be true. That's a question for you. Are we okay with this? So at some point, we're going to need these topics, mostly countable things. So last thing I want to discuss today is equivalence relations. And that's the last thing I want you to know before we can start doing our topology class. So equivalence relations. Let's start with a definition here again. I want to start with the set A. So a relation on a set A is going to be a subset of the Cartesian product. Again, it's a subset. Let's call it R of A cross A. That's what a relation is. And that's not very, very important. What's important here is the following. We say, or maybe we denote A related to B instead of A comma B is in R. And we also use A related to B. We use this if R is clear from the context. Usually you don't put a name to equivalence relations unless you really need to because you have more than one. Otherwise, you just use this \sim in LaTeX. Okay, so we denote that, and now we are going to impose some things here. So we say that this relation R is the following. The first one is, we say it's reflexive. We say it's reflexive if for any element in your A, that thing is always related to itself. A is related to A. Second one is symmetric. We say that's the case if whenever you have two things for any A and B in A, you have the following. Maybe let's say for all A and B, if A is related to B, then B is related to A. And the last one is transitive. And that's triply quantified, A, B, C in A, if A is related to B and B is related to C, then A is related to C. So this one we're going to use at some point, these things. And of course, when something satisfies, if R satisfies all three here, we say it's an equivalence relation. So the idea here is, are you familiar with these equivalence relations? So the thing is, this is in some sense something that behaves like an equality. That's the idea. So the most important thing I want to say now is, I don't want to go too crazy because we're not going to need this very soon. But if you take an element A in your set A, we define, so I'm assuming I have an equivalence relation. We define the equivalence class of A. That's going to be a set. Is the set denoted by this of all things in A which are related to A. So this is a subset of your A. So these are all things that look like your A under this equivalence relation. And something that's very important here is if you have an equivalence relation, you have the set of equivalence classes. So we have the set of all equivalence classes. So now we have the set of all equivalence classes. And in that set, equality translates to relation. So what I mean by this is A equals B if and only if, by definition, A is related to B. So equivalence relation is a weak version of equality, and it actually gives you an equality. That's what I want to say here. An equality in some other space. And that's again going to be very important for us. Very important. So you're familiar with this thing. For example, we're familiar with this. For example, modulo 5, 4 is 9, but 4 is not 9. Right? But you working modulo 5, you get to say the two things are the same. What are actually the same is their classes. Okay, now big theorem about this. So this is another fact. If we have an equivalence relation, A, then the equivalence classes partition A. So what I mean by this is something like A becomes the union. I don't want to use class of A because that's going to be a lot, but something like C, maybe, and C is going to be an element somewhere, and the somewhere, let's call it curly A. And what will be my curly A is this, the set of all equivalence classes. Let's call this set curly A. Now we know this is true. Not only that, we have two of these for this chart. Are we okay with this? Do you have any questions? Okay, so we have 5 minutes. What I want to do in these 5 minutes is I want to say something. Yeah, sorry. Yeah, so this means given, so pairwise disjoint means given C, comma D in A, which is the family of equivalence classes here, if they are not the same, then their intersection is empty. So that means you give me 2 equivalence classes, either the same or different, absolutely different, disjoint. In other words, if you give me 2 equivalence classes with 1 element in common, then they need to be the same, which is sometimes something you can picture like this. This cannot happen. If you have 2, then that's because you need to increase the class. And that's one very good way of thinking about equivalence classes. When you don't have the classes, that's how you compute them.
Kind of like a partition, right?
Absolutely. Yeah, that's how you define a partition. Like these two things, that's what a partition is. Okay, any other questions? Okay, so now let me go and stop my recording because I want to say things that are not very precise.